Well, good afternoon, everybody. Are we all here? Thank you for coming. Welcome to, I guess this is our third now, Headwaters lecture. And in case everybody here knows me, in case you haven't run into me before, I'm Jeff Peterson, Director of the Water Resources Center here. This lecture series is something that we started within the last year, and we're going to be continuing. We'll have probably 3 or 4 of these Headwaters lectures every year. The purpose of this whole series is to bring internationally known, field-shaping water researchers here to campus to interact with the water community here. So where the name kind of comes from is just as, Minnesota is in the geographic space, being in geographic space, it's at the headwaters of 3 of our major river systems in the continent. So too, we'd like to be at the headwaters in the space of ideas about emerging topics in water science. If you didn't know, this lecture series, of course, is co-sponsored by the Water Resources Center through funding we have from CFANS. We are always delighted to partner with other units and other departments across campus. So this time, we're partnering with Biosystems and Bioproducts Engineering. So our guest, Peter Van Oevelen, who I'll introduce here in a moment, was there in their department yesterday and gave a seminar and have met, I think, with a bunch of faculty and folks over there. So if you have ideas in your units and departments for a place where this might fit in, where we could partner with you to bring a well-known speaker to campus, please give me a call. Another thing I should mention before I forget is that we've got refreshments immediately following the seminar today out in the hallway, so don't miss that. And I think Peter, depending on the length of the talk, he can stay for 20 minutes or something like that before he has to head to the airport. Is he thinking that?
Well, for vacation.
Oh, okay. Well, it's an important trip.
Yeah.
And I'd also be remiss if I didn't thank Tracy Fallon, who you saw hit the record button here and is working on getting the refreshments ready out there. Has done a lot of work organizing this, and all the emails and things you've seen and announcements. It's Tracy acting behind the scenes. And also thank you to John Niebuhr, who has spearheaded this and invited Peter here and got a lot of his visit organized. So, without further ado, I am now really excited to introduce to you all Peter Van Oevelen. He's the director of the International GEWEX Project Office, so that's an embedded acronym. The G in there is GEWEX, Global Energy and Water Exchanges Project, and I think he's going to tell you more about what that is and how it's sponsored and how it's structured in his talk. He's a native of the Netherlands, received his PhD from Wageningen University in Earth Observation with an emphasis on microwave remote sensing and soil moisture. He worked in the private sector for a time, started his own company actually, lectured for a time at Wageningen, and then moved to the European Space Agency to be the European coordinator of GEWEX. And became then director of the IGPO in 2008, right? So it's 10 years in his current position now. He's an internationally recognized expert on Earth observation, water resources, and climate change. And in his current role, what he's focusing on, near and dear to our hearts, is facilitating international research, collaboration on water, energy, and climate issues, and making science, in particular science on water and climate issues, more accessible to the general public. So his title is GEWEX Activities and the Water for the Food Baskets of the World Grand Challenge. Good. Welcome and thank you.
Thank you so much. Thank you. Thank you, Jeff, for the introduction. Thank you, John, for bringing me over to Minnesota. So far, I've had a great time, and thank you all for coming here. This talk will definitely not be for the general public, because I definitely would not start it out with some acronyms if that would be the case. So I'm going to talk a little bit about the Global Energy and Water Exchanges Project, which is part of the World Climate Research Program. And the World Climate Research Program is part of another acronym, the World Meteorological Organization, which is co-sponsored by 2 other acronyms, which is UNESCO, the International Geographic Commission, as well as the International Council for science. So I'm gonna, let's see if this works actually. It does not. This is going to be interesting. There we go. So the World Climate Research Program's Grand Challenge on Water for the Food Basket. I'm going to talk also a little bit about PANEX and ANDEX, which are two regional hydroclimate projects, as well as a little bit about some of our activities in the United States. There are many people that are involved in my presentation. Basically, I'm these days a manager, and I don't do that much research, unfortunately, but I try to facilitate. So much of the stuff I present is work of others, and I really have to acknowledge all of those people for that work. So I'm going to talk a little bit about GEWEX and the structure of WCRP and some background. Then I'm going to focus on the Grand Challenge on water for the food baskets of the world, give a rationale, so why are we doing that, how are we going to do that, proposed implementation, and give you some example of the regional focus areas. Feel free to interject me with questions. I'd rather have you actually ask in between here and there, like, hey, what is this? Or if I shoot out an acronym, you're like, what is that acronym? Please just raise your hand and say, what is that acronym? Because I'm so used, unfortunately, now to using all of these acronyms, I don't even realize that I'm using it. And I know I took this job a long time ago and said, we need to change that. And it changed me, unfortunately. So, WCRP Structure. Okay, so the World Climate Research Program is the overarching organization, and under it are a couple of core projects. And one of them is CLIC, that's dealing with the cryosphere and climate. One of them is CLIVAR, probably known, deals with climate and variabilities, looking at the oceans in particular and ocean-atmosphere interactions. SPARC is looking at the upper troposphere and stratosphere. And then we have CORDEX, which more looks at regional downscaling and modeling at the regional scales. How do you translate climate science and climate modeling products to the region? And then GEWEX, where basically I'm the representative here, looks at land-atmosphere interactions. However, we do more than just land-atmosphere, and that probably will become clear. So these projects are sort of guided by a joint scientific committee, and the joint scientific committee is assisted by the joint planning staff to execute, organize the meetings. So basically, if you put it bluntly, the joint scientific committee is a bunch of scientists that sort of talk and have a meeting, and the joint planning staff executes what they want to be executed by that bunch of scientists. Under it, there are some advisory council and working groups, and each of these working groups has a nice other acronym. So I'm trying to avoid all of those. But ultimately, the entire mission of the World Climate Research Program is to better understand our climate, to research processes, and to be able, with that knowledge, to predict what the climate will be like or what we'll do in the future. So, as part of their sort of mission, a couple of years ago, they decided to focus on a couple of grand challenges, and they defined 7. I'm not going to go through all of them, but water for the food baskets is one of them, and that's being led by GEWEX in particular. There's another one, weather and climate extremes, where we are also excessively involved, and actually these two are pretty strongly related in many ways. So GEWEX has some challenges as well, and how do we do that? We look and try to explain the past, understand what's going on now, the present, and then from that knowledge say something about the future. So what is it that we're really interested in as GEWEX as a community? And when I say GEWEX, I'm not talking about me or my project office, I'm really talking about the community that's doing the science. So the big science questions are, where does the heat go? Where's the energy? So when we talk about the global energy and water cycle exchanges project, the energy is solar radiation. We're really talking not fossil fuels, we're really talking solar. How is the fresh water on the planet changing? That's the other question. And the third one, that's sort of a little bit more newer to our realm, is where does the carbon go? And so these things are related, but they also have something else in common, is that they're basically reservoir questions, right? So how much is there? So how much stock is there, and how do we take stock, and how is that stock changing? And GEWEX focus on that, and that's in the realm of what the World Climate Research Program is doing, is answering the question, how does weather change with climate? What does that mean? And how does climate influence the habitability of the Earth and its regions? And of course, what is the effect on humans? I must say that we do focus more on the effect on humans and society than we do actually specifically on the environment. And that's, I think, sort of an intrinsic thing. As humans, we tend to do that. I don't think that we purposely want to do that, but a lot of times when we say that, we say we're looking at society, but really you want to say habitability, not just for humans. So it's in general habitability for other species and plants as well. So seamlessness is sort of what we're going for. We want to understand the processes on all time scales, and we don't want to separate them out. We want to really understand what's going on from the really small time scale events to the larger, centennial type of processes. GEWEX does that research using 4 panels, and I quickly introduce them. We have the data analysis panel that looks at the global data sets. So we produce within the GEWEX community data sets like the Global Precipitation Climatology Project, like the Surface Radiation Budget. Anybody who does any modeling most likely will have encountered the products that are produced under this panel. And it not only fosters or facilitates that production, it also fosters the assessment of these products. So we don't look at just one precipitation product. If there are multiple out there, we say, okay, what is the difference between them? And it's not a ranking like which one is best, because I think that doesn't make sense. We really say, what are the differences? Where can you use them? Where should they not be used? So one example, for instance, is that some of the longer-term data sets should not be used for climate trend analysis. So yes, they're long-term, 30, 40-year records. They show trends, but why do they show trends? Probably because they use a whole bunch of different instruments and they try to make it one continuous product. But by doing that, they introduce artificially trends. For example, I'm not saying that all products suffer from that, but it is something you have to be aware of. The next part is gas, which looks at the atmosphere, and it's called the Global Atmosphere System Study, really looking at atmospheric dynamics, cloud processes, and that sort of thing. And then glass goes down a little bit further, looking at land-atmosphere interactions, so subsurface processes, soil moisture, groundwater, etc., up to basically vegetation into the atmosphere. So that's your first connection to the higher atmosphere. And then the GEWEX Hydroclimatology panel is our way to actually connect all of this science to the regions, to the communities, and to the network. So that's basically where we build our interfaces with various other communities that often are not scientists. So the approach is for us is that we want to be consistent. Really, one of the things that we sort of take as motto, consistency is our way of life. Whatever we do, we have to make sure it makes sense and is consistent. And the integrated approach we try to do is try to quantify the links between energy and water, and we do that through stewardship of observations. So not only the satellite observations I talked about, but also in situ observations. We try to stimulate in situ networks. The baseline surface radiation network is one example. The International Soil Moisture Network is another one. So there are a bunch of them where we really try to either start it, we either facilitate it, or we actually promote it and try to make sure that funding is available to continue that. Furthermore, we try to advance our process understanding. So a big part of what we do is, okay, how do these things work? The intrinsic things of our climate system and weather system, but how do these processes work? For that, we need to do modeling, we need to do experiments, we need to combine different types of observations in various scales. And then the last part is global and regional model. With that understanding, we try to model it, we try to explain the past, try to see how well we do for now, and see what can we say about the future. A big part of GEWEX is satellite observations. And that is one of the big reasons is that GEWEX got initiated in the late 80s, early 90s, sort of when the big push from NASA was in the Earth Observing System, EOS. And there was a need for use of that data. And the World Climate Research Program saw that also as an opportunity, and they basically came together and said, well, we can have this activity that uses this satellite data and for climate modeling. And hence, this is where basically our origins started with producing these data sets with stewardship of the observations, etc. But we're not the only ones doing that, but we are a big part in that community. So with all of that in the background, I can talk forever about the structure and stuff. And let's talk a little bit more about some of the fun. Why are we doing this? And a couple of years ago, we said, okay, we need to try and challenge where water is important. There are a lot of things that water plays a crucial role, basically anything we do. So we'll say, okay, it has to be strongly geophysically based, so it has to really connect to the core of our activities. But at the same time, it has to be attractive to those that really are not part of our community, that understand why are we doing this fundamental research, why are we doing that. So we said, okay, maybe we can do something with food production. And we were talking about trying to get Eastern European scientists more involved into our community. And one way was looking at, okay, is there a regional area where we can work? And it turned out the Pannonian Basin, which I'll talk about a little later, was such an area. And I hadn't heard of the Pannonian Basin, and I doubt that you had, unless you were yesterday at my talk and might have heard it. The Pannonian Basin is not a very well-known region, but it's basically an area in Hungary, primarily Hungary, surrounded by a couple of other nations that was the breadbasket in the 1700s, 1800s, and got drained to actually produce a lot of food, particularly wheat, for a big part of the European region at that time. It is a very unique area, has been drained, so there's a lot of human influence, which we're looking for. It's related to food, which was the other thing that was attractive, and it also has a very stable bound regulator a lot of times per year, so it has some very interesting atmospheric processes. So with that in mind, we came to the conclusion of water for the breadbaskets of the world. So I went out and gave a seminar in, I think it was Tokyo, and people were like, why is it breadbaskets? You know? So, and rightfully so. Yeah, sometimes you get smack right concentrated with devices. Indeed, food, rice, wheat, you know, similar thing, but not the same. So definitely, we said we need to change that so it became water for the food baskets of the world. So what do we try to do with this? Is really, you know, it's a nice grand name, but ultimately, as geophysicists, hydrologists, we're interested in improving our models and using that, our modeling capabilities, and actually say something about the future. So that's the idea. So food production is sort of the key element, right? We said for the food basket. So why should we then worry about water? Well, first look at food production and what are the key issues. So we know that the general population will be increasing, and by 2050 it will be roughly 9 billion. So we have to increase our food production to keep up. We all know that food production will use more water. We also see, actually, unfortunately, that the increase in our food production is slowing down. So yes, we are still producing more and more food every year, but it's slowing down. We're not keeping up with the increase in the population. We're also not keeping up with some other aspects I'll talk about later. So population growth is a big issue when we talk about food. We need to feed them. Globalization is another point, is that, yes, where do we grow food? How is food exported? How does it go around? Urbanization. Yes, a lot of people are sort of concentrated in certain small areas, and we need to transport the food to that area. So you have things like conserving foods, making sure that it doesn't spoil. Water scarcity, yes, that's an issue, and you see that droughts, etc., planting season, timing, etc., and you need to have enough water. Declining yield. A lot of crops are returning less yield per acre. Why is that? Can we do something about it? Climate variability and climate change, absolutely. Yeah, they will have an effect. What is that effect? So there are many more of these things, and you can read them. But basically, for our interest, water scarcity and climate variability and climate change are sort of the main things we're going to look at. So agriculture and fresh water, there's another big issue related to that, is that agriculture uses about 70% of the global freshwater resources. So on the left picture, on top left, you can sort of see how that's divided among the several regions. So in the West, Europe, and Central Asia, agriculture industry has sort of domestic, have relatively the same amount of proportion. But if you go to Asia and Africa, it's more than 90% of the water is being used for agriculture. So yeah, that's used. That's a big time. In addition, if you're looking at agriculture and you're looking at climate change, it's about a quarter of the greenhouse emissions are coming from agriculture. The Earth land mass is about 40%, 37% is being used for agriculture. And the water withdrawal, so the use of water, is about 70%. So you can see that the agricultural sector and water are very, very crucial in basically our environment and how that interacts with climate. So if we want to feed 9 billion people by 2050, and that means about 50% increase in food production, and that unfortunately will probably lead to a 15% increase in water withdrawals. So I would take those numbers a little bit with a grain of salt, in the sense that there might be much more, might be much less. But we'll see the trend going in that direction. We will use more water, depending on how we're going to do our agriculture in the future. And we will see an increase in agricultural production, but can we meet that 50% or not? That depends. So that comes to the next point, is sort of like, how do we get there? What are the main issues? Food security relies on four main things. And when I put together this presentation for the first time, we had four key issues: availability, access, utilization, and stability. And both access and stability were the obvious one, where we say climate change has an effect. However, some recent papers show that the nutritional status of our production is actually going down with an increase in CO2. So it's also, that one is something that climate change affects. So yes, more CO2, you have more greening, you have more production, but your nutritional value is going to go down. So that's a very important aspect, because not only are we going to be more people, we're going to all be richer, and when you get richer, you want to have more, better food, meaning high protein food, more nutritional value. Unfortunately, that is just a thing that also goes down. So we have a couple of factors that are really working against us when we're trying to solve this problem. So the impact of climate, how does that work? Well, CO2 and temperature just sort of indicated, yes, we have greening, we have more, in certain areas definitely more vegetation. Globally, we will have more vegetation, but globally we'll probably see a reduction in food production. Pest and disease with rising temperatures will increase. I think in the US, we're all also aware of the fact that a lot of these insects are now globally transported. Sting bugs is one of them. The emerald ash borer is another one. I think the latest one that is going to be is the lantern bug that's now in Pennsylvania. That's going to be a big issue for crops in the eastern part. So bugs are going to be really, pests and disease are going to be really an issue. With changing climate, the extremes will most likely increase, and hence things like drought and flooding will also be more common. And water availability hence will be drastically changing. In some areas you will have too much water in the wrong time. In a lot of areas you will not have enough water at the times that you, for instance, want to plant your crops. So having raised sort of the importance and why it's an issue, we can come up with some counter examples. So one of them I already talked about, carbon dioxide. But another one, if you're looking at the Netherlands, okay, small country producing a lot of food, relatively. I looked it up because somebody yesterday, is it by tonnage, no, by value? It's by value. They're also quite a high producer by tonnage, but definitely not, of course, in the league of China or Brazil or the US. However, these countries, they produce a lot, but exporting-wise, I think it's the US that's first by tonnage, and then it's Germany and Brazil. They're really the big producers. But the Netherlands, a small country, is by value the #2 food exporter. And how do they do that? Greenhouses. So recycling water, so agriculture in the Netherlands is actually using less and less water. They're also, by doing this recycling, they're actually recycling the nutrients, so they can keep that up. They have different types of crops now, so different types of tomatoes and different types of peppers and chilies. I didn't know that the Netherlands was also the #1 exporter in chilies. Who would have thought? So maybe the link to Indonesia has something to do with that. So yes, there are ways to increase our food production, but can you move that model to other regions? I mean, does it make sense? What does work? I think I had this morning a discussion. You know, if you're looking at California, yes, you cannot put almond trees in the greenhouse. So that sort of crops, is going to be different. Fruits is going to be more tricky. But a lot of vegetables you could tackle through this way. But wheat and corn and rice, no. So we have to still come up with some solution. Then, not unimportant, I would say, probably even more important on the short term are the socio-economical effects. So climate change will have an effect on the long term and will really affect a lot of things, but much of the decisions are really driven by the socio-economic factors. Primarily, a farmer will have to make money. Livelihood is a key issue. That's the way they make their choices. So how do we interact with those type of systems? We can have a nice model, we can incorporate all of this, but then what does it mean when we don't include the socio-economic effects? So starting point is, looking at all of this, okay, how well do we know the water cycle? Is the water cycle still natural? And I still raise it as a question here, but we can answer that basically, no, the water cycle is not natural. We are really affecting it in many ways, not just by irrigation, extraction, and dams. We're also changing the land surface, changing so many things that wherever you go in the world, the water cycle has been affected by humans. Even if you go in the Amazon, you will see effects by humans on the water cycle. So we need to incorporate that. And up to very recently, I think most of us hydrologists were looking at it as a completely natural system with hardly any, and certainly on a global scale, with hardly any human influence. How well do we know the processes governing the slower reservoirs in particular? This morning, some interesting talks with some of the students here about groundwater. And that's one that we really want to take stock of, like how much groundwater is there and how is that changing? How is it with the glaciers? How are they changing? How is the snowpack changing? And how will changes there affect basically the water cycle? Climate change will perturb the real system, but how relevant is that actually when we have the socioeconomic factors being such a big driver in a lot of our decision making? So what's the relevance? Where does it play? Where is the importance? And then practices for instance, water resources management are based upon what happened in the past. So how valid are past experiences for the future? We can treat it as a stock market, and the first thing they say is past returns are not a guarantee for future, right? So similar here is that we can do all of that. We can model the past. We can really do well in the present. But, okay, what is the value for the future? So we really have to get a better handle on that. And doing all of that, what's the relevance for the practitioner? Does the farmer even can use this? So you really have to make sure that whatever you do, that has practical relevance. And how do we make that knowledge transfer effective? So basically, the water challenge is water cycle is the main driver of food production. It's not the sole driver; it's one of the main drivers. A warmer climate pushes the water cycle into unknown territory, so you have to figure that one out. The terrestrial water cycle is definitely not natural anymore, and there is an urgency to understand that new state, both with the natural and anthropogenic components and how they interact. So how are we going to do that? There are a couple of ways. Observational-based studies. So yes, we're going to collect the data that's already there, but at the same time, we're going to look for regions that have intense agriculture, where we can have clear footprint by humans on the agriculture, on the water systems, and trying to better understand what's going on. For GEWEX, that means we use our regional hydroclimate projects, better quantify the human control on that, do process studies, and promote interdisciplinary analysis. And really, that last point is very important. We should not be trying to do everything. We really should stick to what we're good at and find those groups that are good at the other parts and actually interact. So interaction, interfacing is our new challenge. Enhancing predictive capabilities is where we want to go to. Propose model comparisons to promote model development. A lot of times model comparisons are done to publish a lot of papers, not so much to get a better model. I'm really pushing that one because I feel super strongly about that. So modeling the comparisons are very valuable, but you really want to keep in mind that the reason why you should do them is actually to make the models better and not to produce papers on how they differ. Revisit the past evolution, which combine climate change and increasing human intervention. We've had a lot of things related to land use and land cover change, so a lot of things out there already. How does that relate to what we're doing now? Do we have to redo some of the things that we did in the past because we have better understanding? So that, and consolidate process knowledge. And that means that we are also starting to link to other communities and other type of modeling. So, as I said, regional hydroclimate projects are sort of one way for us to do that. And this shows you an overview of quite a few of the past experiments we had. So we had a nice, coverage of the Earth in the last 25, 30 years. And currently, we're sort of looking at these regions. The food basket regions we're sort of looking at is the Pannonian Basin, so basically right smack in the middle. The Southeast Asia rice and wheat regions, we're really looking to get something established there. Central Plains, Central Valley, basically both sides of the Rocky Mountains, we're really looking at those, so the food producing regions in the US and North America and in Canada. And Andex, so basically looking at the mountains area in Latin America and see how that's going to change. So the red dots and the red areas are the current regional hydroclimate projects we have active. Andex is a new one starting, so we're really getting going there. HIVEC, I'm not sure what the current status actually is. It was really going well up to a year ago, but it sort of seems to slow down, so I'm not sure where that's going. And all the other ones are very healthy and going in the right direction. We're developing a new cross-cutting activity in the Himalayas to look at water security and food. And along with Southeast Asian countries and Japan, we're trying to develop a new Southeast Asian regional hydroclimate project as well. So if you have interest in these type of things and you're like, oh, wait a minute, how they're doing something somewhere else, this is sort of one way to figure out what is going on. So the Pannonian Basin was sort of the reason why we started doing this, and it's in a very interesting little area, and I quickly go through it just to give you an idea of it. But the Adriatic Sea is in the bottom left corner, and the Carpathian Mountains are on the right, circling, and all these blue regions are basically swampy, flooded areas, and they drained all of that. And if you're looking at some of the, and this is a very low resolution image, you can see that a lot of times clouds really stick around in that region. It's really nicely embedded by these mountains, and it's a very stable atmosphere. So it is for us an interesting area to look at where, for instance, boundary layer processes, how do they interact, and along with the hydrology, it's going to be a fun area to look at. Another area we want to look at is the Rocky Mountains. We have activities in Canada, but we would love to have some more things going on in the US again. So in particular, we try to do more observational synthesis, so improve the snow tell and precipitation measurements in the Rockies, trying to coordinate maybe another multi-scale experiment, and understanding key processes of data to test several model hypotheses, in particular related to convection permitting modeling. And that basically means high resolution modeling where you don't have to parameterize convection anymore, but actually by modeling it at a low scale, actually the model will produce that convection by itself. And for that, you need to go down to scales of about 2 to 4 kilometers. And WRF is the model that's been used to do that, the Weather Research Forecast model. So this is one example on how the terrain looks like at 36 kilometers, which was sort of the standard resolution, and how it looks at 2 kilometers. And you can see that if you, for instance, compare that to the observations, what the difference is in how well you can actually start matching the various snow observations. But even more importantly, when you, and I hope this thing starts working or not, yes, there it is, you can see when you go from high resolution to low resolution, how the topography basically gets smoothed out, and what that does to your atmosphere, because, you know, that surface is really disappearing, becoming much smoother, and that means that a lot of these interactive land-atmosphere interaction processes are changing. So going from that, so 4 kilometers where you still see the mountain ranges to basically the 36 kilometer where it's really smoothed out, has a huge effect. And how huge is that effect? Well, if you're looking at the precipitation, then 30% less precipitation is produced in winter and 65% too much in summer with a low resolution, which is also a little bit counterintuitive in certain ways. But actually, by doing that, your averages go down, but your extreme events are much better simulated. So your variation you capture much better, and that's I think very important. And in addition, which is also I think is even more surprising to me, was that even for transpiration was 38% higher in the lower resolution model. So this gives you to show how important it is to model at higher resolutions, not just because you have more detail for the heck of it, a better picture, but really because you're starting to capture the essential processes that you really need to go explain larger scale features. So that's why the Rockies and mountain hydrology really is capturing our interest. That's why we like to do stuff in the Himalayas. A, we don't have enough observations, we like to see more, and B, because we don't understand the processes well enough yet in many of these areas. Secondly, I think when we're looking at convection permitting modeling, there are a lot of things that are improving. So, for instance, if you're looking at what amount of water is available, the precipitation minus evaporation, as you saw from the previous example, in higher resolution models, you get a much better estimate. The other thing that we want to look at is that we're using, when we're looking globally, these evapotranspiration reference formulas, and they're empirical. And so, how good are they? Well, it turns out they're not really good, and there are a lot of comparisons going on, but we really need to do better if you want to look at the global scale. So moisture availability is strongly driven by factors like rainfall intensity. So having your precipitation events better modeled gives you a much better idea of what the state of the surface is, and that's important not just for soil moisture availability, but also for things like landslides. So with a coarser model, it's much more difficult to model those type of things. So there are many reasons why we should do that. I'm not sure how I'm doing time-wise. I should start closing up. So with that knowledge, we said, okay, we don't have enough regions where we can test this, and the Rockies is one place where we can do it, the Alps is one other place. So are there other regions where we can actually use this type of modeling? And one area we're trying to go look at is the Andean region. And why would we look at that? Well, one of the reasons is that, like many other mountainous regions, scarcity of observations. Secondly, it's a community that we don't interact with so much. So for us, as an international research facilitation group, we really want to be inclusive and have more access to different networks and different people. So this is one way for us to connect to the Chilean hydrologists, to the Argentinian ones, to the Ecuadorian ones, to Peruvian ones, to Colombian ones. It really helps us in growing our activities. And also, that helps us in getting better products, because now we have different regions where we can validate not only our models, but also our global data products. So the last really important part is that doing water for food means that you have to look at food production and food modeling. So you have to link to agricultural modeling. And this is something that really probably becomes one of the key issues in what we're doing is how do you link hydrological, weather, and climate models to growth models, vegetation growth models. So this is going to be an interesting area to interact with, because currently we run them independently and use one to feed into the other. But of course, your hydrological models use different assumptions on the land surface state than your vegetation models, and they should be the same. So these are some of these simple things that are logical, but they're not done yet. So we can do much better, and we should do much better. Some examples of research topics on land use and land cover change. That's another area that, of course, becomes logically part of this. What we expect out of it is progress in land surface modeling, of course, with the explicit representation of water management in the broader sense. Enhance our knowledge of surface-atmosphere interactions in managed environments. Build the capacity and capability to predict the real system, at least for the regional scale and at least at weather time scale. So we're not going to pretend that we can do decadal, let alone centennial with this, but at least in the shorter seasonal to annual time scales, we should do better. Develop our capabilities to predict the water and nutrient fluxes to the ocean, and make climate sciences more relevant to hydrological and economical sciences in terms of processes and scales considered. Because as a climate research community, there has been traditionally disconnect with the hydrological modeling community. So that we can do better as well. And that's sort of roughly, I think, what we expect to come out of it. What I should add is that, yes, important is interfacing with socioeconomic aspects and those who model that, as well as the agricultural part. This is something that you need to put in every report. Is how important is it related to the Sustainable Development Goals? I think when you talk about water, it's kind of hard to make a choice, actually, because it intersects with basically all of them at some point. But we sort of said, well, in particular for zero hunger, when we're looking at food production, clean water and sanitation, sustainable cities, a responsible consumption, climate action, and life below water and life on land are sort of the main parts that we are focusing on. And with that, I think I sort of talked 40 minutes, so thank you. And if you want to know more, you can contact me or my office at that address. And I also have to thank NASA for their continued support for more than 25 years in actually making this possible. So that I also always want to conclude with. And thank you so much for your attention. And I'm hoping that I get some questions.
Peter, if you wouldn't mind repeating the question you get just for people who are watching online or
Sure, no problem. Yeah. Okay.
So if somebody wants to get involved in one of these many projects, but they're just one person or a small, very small team that doesn't have any money, but they want to figure out how to get money. I know that you don't fund things, but is there an advantage to going through GEWEX? I mean, if they want to get collaborative, there's all this modeling activity, there's all these challenges, and it seems like there's a lot of opportunities for people to get involved somehow.
Yeah. So how to get involved in these activities? That's basically the question. I think one thing, if you're interested and want to do something, or you want to connect your research to what's happening here, is contact us. So we can sort of say, what are you doing? Where within the GEWEX community does your work fit best? And then we hook you up with people that are working. The other thing is by using the data or using things from our community, you can basically give feedback. Say, hey, I'd like to know more. That's a really natural way to get involved. Use the data or use the models and start interacting. But we can help you as a project office, because that's our job, in sort of figuring out what the best way is. When you're sort of involved or you're already familiar and you want to step up a little bit, you can nominate yourself or let yourself be nominated to be part of the panels or the steering group. I would say that for the junior scientists, we're really trying to get early career researchers involved. Personally, I must say that I do think that, focus on doing research this part of your career as much as you can. Don't get bogged up in the politics of steering groups and panels too much. But at the same time, it is an opportunity to get exposed to others and other research. So there are pros and cons, but I always say do it, but don't let it go at the cost too much of your research. Keep that in mind. So hope, John, that answers your question. Good. Yes.
The question I still don't understand the way, but not the whole protein thing. I heard people say, well, there's an impending food crisis. Is there a food crisis or is there a meat crisis?
No, it's food. I'm not a person to say food crisis. I mean, I don't think it's my job as a hydrologist to make any statements on that. But from sort of the latest literature, what you're seeing is that it's not just that the meat consumption needs to increase because people like to eat more meat and high protein value, but it's also apparently that our vegetation, so your cereals and your vegetables are getting lower in protein, lower in nutrition. So that's an issue because that also feeds into the cows and the meat. So it's double whammy in that case, is that your meat production will probably go down because your quality of your food for the animals also goes down, and the direct quality of the food for humans, the vegetation part, the green part, is also going down. It's still, I think, they're now trying to figure out what exactly, how big that effect is. So I'm not a modeler in that area, I'm not an expert for the whole, but yeah, it is becoming an issue, definitely, certainly long term. I saw the back there, yes.
So that's a Maryland area code, so there's NASA and NOI and USPS on there. Can you talk a little bit about how your work for the projects are interacting with some of that other, like downscaling?
Yes, I repeat that. I thought that, absolutely. So how does our project office interact with, since we're in the DC area, interact with all the agencies? I think that's, in short, your question. So GEWEX has been started in the late 80s, early 90s, and NASA was a big proponent of that. So naturally, also because the project office is funded by NASA, we have a very strong relationship with NASA. At the same time, some of our past regional hydroclimate projects were very much driven by NOAA and the NOAA Climate Program Office. We have strong links to the Department of Energy and what they do with respect to modeling. NSF, of course, sponsors a lot of research. Since we're not a funding agency, the only thing we do is facilitate and sort of try to, assist program managers with, these are the key issues where you could look at and where funding would be appropriate. And that's how we interact with NSF, with NOAA, with DOE, all those. That's within the U.S., but we do the same thing with ESA, we do the same thing with JAXA, we do the same thing where we can, either through the World Climate Research Program with the European Commission and the European Union. So we really try to, make sure that our research agenda is being heard and seen as relevant, and that national funding agencies are willing to spend money on that. So, good. Got that question in front there. Yeah.
So I noticed that a lot of the research areas focused in this region. It seems like part of that you explained as the models essentially being inadequate because they're not quite enough resolution. I guess I just wasn't making the connection. The goal is to improve food security. Are we that dependent on the snowpack in these regions?
Well, so your question is how a lot of the research I showed here focused on mountainous regions. I probably have to sort of clarify it a little bit more. And then the follow-on question was, how does that relate to basically food security? Because are we so much dependent on water in the mountainous regions? To start with the last question, yes, we are. In many ways, if you're looking globally, then the Himalayas as well as the Andes provide basically much of the water for the population surrounding those areas. So yes, in Europe, to a certain extent too, is it related just to snowpack? No, but it is related to precipitation and snow and the glaciers that are available. But the interaction between that is much more complex. So I wouldn't say just snowpack, because in certain areas it's actually the rainfall that falls in the mountains that just runs off and contributes. We focus on mountainous regions because it's more and more clear that we need more observations in the areas. It's so hard to get well-established networks. So that's why we focus on it. But some of the regional hydroclimate projects I showed, we're also in the Baltic Sea region. One of them was in the Mediterranean. A lot of, for instance, what happens in Canada is actually in the plains in Canada. So we're not just looking at the Rockies. Definitely is a huge part is the Canadian plains. So no, we're really looking globally. But I was emphasizing here, because mountains are becoming more important, I think also internationally as an important topic. WMO will have its mountain summit. So we're really trying to push now, see there's an opportunity to get a couple of activities going where we improve our observations, improve our modeling, and get more information out of these difficult regions. Yeah. Good, thank you. Yes, please.
You mentioned that your research at GEWEX has social, cultural, or socioeconomic implications. I wanted to talk a little bit more about that, and then how that incorporates the project
So the question is, how does GEWEX deal with the socioeconomic impacts or the relationship with our work to socioeconomic aspects? So as I pointed out, we're geophysicists, we're hydrologists, meteorologists, so we're not socio-economists or sociologists, and hence we shouldn't do that, and we don't have the intention to do any of that type of thing. At the same time, we have to realize that a lot of what we do, is in service of society, so it will be strongly related to society and economics related to that. So our interest and our desire is actually to have better interfaces with these communities and better understand what they desire, what they need to fulfill their agenda. And I hope that some of this stuff, when we talk about water for the food baskets, can have an overlapping interest where we say, okay, our interest is in actually incorporating and better understanding the human dimension, and can you help us in actually understanding those aspects of the human dimension, the information about, yes, water consumption, because that's a lot of times economic driven. How can we measure that? Can you give us information on that? So that's a very basic start on trying to get a handle on it. Going further is, can you help us when we have these models, we have that incorporated, it works. How can we use that actually to quantify the water use in the future? How can we predict the future? As I pointed out, I think that the socioeconomic aspects are so much more important, certainly on the short term, in what decision making leads to, that we should be a little bit more modest in what our models can do, and hence it's very important to make those connections. I think today, like having a talk with Jeff here, for instance, with his background, those are the things that we want to have. People that are familiar with economics, know hydrology, so you can talk the language and start from there and start spreading out. So I hope that answers your question. Good.
Just a curious question, but maybe we were off topic. As a hydrology ecologist yourself, how do you think that your Americans' agriculture system can be improved so that the breadbasket of the North America can be more secure?
Okay, so your question is how do I view that the American breadbasket or food basket can be improved? That's a big topic. I think staying to my own area of expertise, which is hydrology and Earth observation, I think, and I always said that, is that much of the issues in the U.S. are related to legislation. We have many solutions to many of the water problems in the U.S. The question is, can you implement them? Can you actually get them there? So the other thing is, are we allowed to, as researchers, to use all the available data that's out there to do better research and get access to not just the runoff, but also all the groundwater, all the use of irrigation, the hydropower, that stuff. So there are many aspects where we can improve, and to try to answer that question, I think improving the American system, you are the #1 food exporter in the world. So in that sense, you're doing pretty great. At the same time, I would say that yes, the stress is in California now. Okay, what does that mean for the cost of food for the rest of the U.S.? Because we know that water isn't a big issue, and it's becoming a bigger issue. And with the fires and the droughts, how is that going to impact food production within the U.S.? But it's a very big question you're asking there, and I'm just trying to say that we try to answer that from a geophysical perspective, saying, yes, we can model certain things. We can say how you can improve water use in these regions. We know how to do better irrigation. We know how to reduce groundwater use. But as long as there is a legislative impediment in how that water is being distributed, there's not a lot that you can affect. Okay, thank you.
Well, that big topic might be a good one to continue discussing out in the hallway, along with other questions you perhaps didn't get to. But especially since Peter is on the schedule, I might just a few minutes early, but it's probably a good time to conclude the discussion in here and adjourn, and we can have a little bit of Thank you, Peter. Let's thank him.
Thank you very much.